Have you ever really stopped to wonder what's going on inside that phone in your pocket or the laptop you're using right now? I mean, it seriously feels like magic, right? But it all boils down to a processor, which is basically a really, really smart rock. In this explainer, we're going to pull back the curtain and demystify how that rock actually thinks. All right, let's get into it. So here's the fundamental problem we have to solve. We think in these complex, messy, nuanced languages, like English. A computer, though? It only understands incredibly simple, direct commands. It's just ones and zeros. So how in the world do you translate a complex thought like, hey, show me a funny cat video, into a language that a tiny piece of silicon can actually understand and execute?
Well, it all comes down to translation. You need a bridge, right? A special kind of dictionary that connects our human world to the computer's machine world. And understanding that bridge, well, that's the very first key to unlocking how a CPU, the brain of the computer, really truly works. And that bridge has a name. It's called computer architecture. The best way to think about it is like an official blueprint of the computer's capabilities. It's not about the physical wires or the circuits, not really. It's about the rules of engagement. It's what a programmer absolutely needs to know to get the computer to do what they want. This brings us to a really key distinction. You've got architecture, which is the what. What does the system do? What are its functions? Then you have organization, which is the how. How is it all put together to actually do those things? For a programmer, the person writing the code, the only thing that really matters is the architecture, the what. So let's get a little more specific. What does this computer language actually look like? Well, the answer lies in something called the instruction set architecture, or ISA for short. And this is where things start to get really interesting. The ISA is, quite literally, the complete list of all the words the processor understands. We're talking commands like add this number, multiply that number, or move this piece of data from here to there. It's the official, non-negotiable vocabulary that forms the ultimate link between the software and the hardware. You know, just like any good human language, a good ISA has certain qualities. It's got to be complete, able to do anything you ask of it. But it also has to be concise enough to be manageable. I mean, you wouldn't want an instruction that only adds the number 15, right? That's way too specific. The goal is to be simple, generic, and powerful. But here's the twist. It turns out there's more than one way to design a language like this. And that has led to a major split in design philosophy, creating two very different schools of thought on how to build a computer's vocabulary. Okay, on one side, you have what's called RISC. Think of it like a chef's set of really good kitchen knives. You've got one for chopping, one for slicing, one for paring. Each tool does one simple thing perfectly. On the other side, you have CISC. That's more like a Swiss Army knife. One tool that has a corkscrew, a screwdriver, a little pair of scissors, all packed into one complex gadget. This is exactly why your phone, which needs to be crazy power efficient, uses a RISC-based ARM processor. And your powerful laptop, which has to run decades of complex software, often uses a CISC-based Intel chip. It's our first big hint that there's no single best choice here. It's all about trade-offs. So, which one is better, the set of knives or the Swiss Army knife? Well, to even begin to answer that, we first have to agree on what better or faster actually means. Because as it turns out, there's more than one way to measure a computer's performance. See, when you click a button on your screen, what you care about is response time. How quickly does the thing you want appear? That's what a user feels. But if you're running a massive data center for a company like Google or Amazon, you probably care a lot more about throughput. How many total jobs can the system finish in an hour? And these are two very, very different metrics. To really see why this difference matters so much, let's use a quick analogy. Imagine we're running a car factory. Okay, so the response time to build one single car from scratch, from a pile of parts to a finished vehicle, might be 4 hours. But if you have a super efficient assembly line, a brand new car could be rolling off that line every 10 minutes. That's a throughput of 6 cars per hour, even though each individual car took way, way longer to build. So what's the big takeaway here? You can have fantastic throughput even with a really long response time. The two are not directly tied together. And improving one doesn't automatically mean you're gonna improve the other. All right, so for the rest of this, let's focus on what a user feels most directly, response time.
How do we actually break down what determines the time it takes for a CPU to complete a single task? Well, it all comes down to three core ingredients.
So what are they? What are these three secret ingredients that computer architects are constantly mixing and matching to cook up better performance? Let's take a look. First up, you've got the instruction count. Just think of this as your to-do list, right? How many steps are in the recipe? Second is CPI, or cycles per instruction. This is the effort each step takes. Is chop vegetables a single quick action, or is it a more complex one? And finally, there's the clock cycle time. That's simply the pace you're working at, how fast you're performing each of those individual actions. So the relationship is actually pretty simple. The final CPU time is just these three things multiplied together. To make a program run faster, you have to reduce one of these factors. The real challenge, though, as we're about to see, is that they're all connected to each other. And this brings us right to the core challenge for any computer architect. It's not about just maxing out one metric. It's about a delicate and often really difficult balancing act. Here's the catch, you see. These factors are all tangled up together. Remember our RISC versus CISC debate? A RISC processor might need more simple instructions to get a job done, which increases your instruction count, but each one of those instructions is so simple it takes fewer cycles to complete, which lowers your CPI. It's a classic trade-off. You pull one lever and another one moves. And believe me, the puzzle is even bigger than that. Architects are also juggling cost, how much power it's going to consume, software compatibility, and of course, what the computer is actually going to be used for in the first place. It's a massive, multidimensional problem with no easy answers. And this really brings us to our most important takeaway of all. There is no single best computer, just like there's no single best vehicle. A Ferrari is awesome, but it's terrible for hauling furniture, right? It's all about designing the right tool for the right job, with a unique set of compromises that make sense for that job. So in the end, the quest for performance is this incredible puzzle with no single perfect solution. And as technology keeps evolving, architects are just going to keep finding new, creative ways to balance all these trade-offs, creating new pieces for this ever-changing puzzle. The real question is, what will that next piece look like?